Section 2.8, the derivative as a function. Previously, we saw the following definition for the derivative of a function f at a fixed number a. F prime of a is the limit as h approaches 0, f of a plus h minus f of a divided by h. If we instead let a vary and replace it with x, we have the following formula. We can now regard f prime as a new function called the derivative of f. The value of f prime at x is the slope of the tangent line to the graph of f at the point x f of x. So, for example 1, the graph of a function f is given below. Use it to sketch the graph of the derivative f prime. We can estimate the value of the derivative at any value of x by drawing the tangent line at the point x f of x. For example, look at x equals 5. We have drawn a tangent line here, and we know that the slope is 3 divided by 2. So we can plot the point 5, 1.5. Do you see where the slope is 0? These spots will be where the derivative crosses the x-axis. Since f of x is positive between a and b, then f of x is also going to be positive. Same follows for between b and c. Since it is negative, it will be negative between b and c. Alternative notation. Using y equals f of x to show that y is dependent on x, the following are alternative notations for the derivative. So a function f is differentiable at a if f prime of a exists. It is differentiable on an open interval, ab, or a to infinity, or negative infinity to a, or negative infinity to infinity. If it is differentiable at every number in the interval. If f is differentiable at a, then f is continuous at a. So the converse of this statement is false. Not all continuous functions are differentiable. So here's an example. If f of x equals x cubed minus x, find the formula for f prime of f of x. So we practiced this a little bit in class on Thursday. So f prime of x as limit approaches, h approaches 0. So what we do is we simply plug in x plus h into every x. So it's going to be x plus h cubed minus x plus h minus f of x, which is in the entire thing. With a little bit of algebra, we can simplify down to 3x squared minus 1. Now we can check with the graphs. So look at f prime of 0. When f has horizontal tangents and f prime of x is positive when the tangents have a positive slope. Therefore, we can check with our calculator. We can use our calculator to graph these graphs, and we can check that since this was 0 right here and this was 0 right here, that's going to be the places where the derivative crosses the x-axis. And since it is negative between those 2 points, it will be negative or below the x-axis between those 2 points. Now find the derivative of f of x equals the radical of x. So state the domain of f of prime of x when we get done. Here again, we simply plug in x plus h into our radical x, and then we subtract our radical x all over h. And then we evaluate as h approaches 0. With some magical little algebra steps here, we know that this is minus square root of x, so we're going to have to times it by what we can call the conjugate, which just simply means leave the algebra alone and change the sign and multiply by top and bottom. Because essentially here we're just multiplying by 1, so this is allowed. And then we continue to simplify down and we get to 1 over 2 radical x. So if we look at the domain of that, we can see that anything greater than 0 works. So the domain of f prime is 0 to infinity. Neither one of those are included, because 0 times 2 would be 0, and that would be a problem. Example 4. Find the derivative of the function using the definition of the derivative. State the domain of the function and the domain of its derivative. So here we go. What is the domain of this? Well, it would be negative infinity to infinity. And I'm not going to go through the formula yet again, but I would like for you to check that you could find that the derivative is 10x plus 3. And the domain for both is going to be negative infinity to infinity. Then again, here's another formula, 1 over x squared. I would like for you to try the formula on your own and check and see if you get the answer, negative 2 divided by x cubed. The domain of both are going to be all reals except for 0 because we cannot have a 0 on the bottom in either of our functions. So example 5 looks at an interesting case. F of x, the absolute value of x minus 2. So here's our graph of that. And f of 2 does not exist because if I were to pick a tangent line on this one right here at f of 2, I could draw it this way or I could draw it this way. So the question is, well, which one do I pick? And guess what? When you have a choice, there's no derivative. It's that simple. There is not one that is better than the other, so no derivative exists right there. I mean, no derivative exists in this line. So if it comes to a point, no derivative. We have some other special cases. To determine the values at which a function f is not differentiable graphically, think about tangents to points on the curve, like our previous example. In general, if the graph has a corner or a kink in it, there's no tangent line right here. So Mo was correct when he mentioned in class that he thought this was one but couldn't remember my. And the reason is because there's a kink in it. There is no tangent line possible at this point, and the function isn't differentiable there. Also, at any point of discontinuity, if I can say that word, discontinuity, f fails to be differentiable along with any point that has a vertical tangent line. So as you can see, both of those, these would not be differentiable. Suppose we want to start with the following function. F prime of x is going to equal 15x squared minus 6x plus 10. Notice that this is also a function, so it can also be differentiated. Therefore, we can find the second derivative, and we denote that by making 2 derivative marks here, and we get 30x minus 6. So, this is called the second derivative, and f prime is now called the first derivative. Since this is also a function, we could differentiate it again and get the third derivative, which would be, with all this funky little notation, f with 3 prime marks of x equals 30. And finally, the fourth derivative, f prime of x equals 0. Note that if we continue from here, all further derivatives are also 0. So here's some notation for the second derivative. In general, this is true. Now let's find an example. In the first example, we found x cubed minus x to be 3x squared minus 1. So now we can find the second derivative. And once we plug it into this formula and go through this formula ourselves, we get the second derivative to be 6x. Then again, if we really wanted to, we could find the third derivative. The third derivative would just simply be x, and then the fourth derivative would simply be 0. So, derivative's the easy way. I know some of you know this, so here's one way, after practicing the formula, that you can use to solve derivatives. So, if f of x equals c, well then the derivative of that is just 0. So, any constant turns into 0. If f of x is a variable, then f of x is the exponent. In this case, it is 1. Same here, x squared, then derivative is going to be 2x. X to the cubed, it's going to be 3x squared. So there's a little imaginary 1 here, but the instance is it's n minus 1 when you take the derivative. So you can follow this theorem right here, or you could use the formula that we have. On a test, I will probably require to use the formula and this theorem, so you need to practice using the formula. Find the derivatives of the following functions. This slide I'm going to leave up for you, and I want you to practice that and learn the ways. Next, I'm going to give you 2 more derivatives that we will practice in class. So here's some extra theorems. Take notes on these and bring them to class, and we will continue to practice. Done. Do WebAssign.